Hello there. In this session, we will talk about top and bottom conditions in Anaqsim models. We've already talked about external line boundaries, which define lateral conditions to the sides, the edges of the model to the side, but we need to talk about how you set up boundary conditions on the top and the very bottom of your models. And there are two kinds. You can specify the flux rate, like a recharge rate. You can also have a head-dependent flux, like leakage to or from the bottom of the surface water. I'll give some examples of how you specify those things, and we'll talk about area sinks in a very introductory way. Two kinds of area sinks, uniform and spatially variable, and these are different than, say, point sinks, which are wells, or line sinks, which can be internal line boundaries like a river or something like that. These instead spread the discharge out over areas. And we'll talk about some possibilities for abrupt changes in your top or bottom conditions. Maybe you want the recharge rate to change abruptly at the edge of a leaching field, for example. We'll talk about surfaces if you want to have top or bottom conditions that vary with location within a domain. We've talked a bit about line boundaries, and one class of them were the external line boundaries that form the lateral external bounds to a model. So, for example, in this illustration here of a model that's single layer in the domain A region, and then 3 layers here in this BCD region, there are external line boundaries all around the outside of domain A here, and they could be various types of external line boundaries. And then on the external stretches here of domains D, C, and B, there would be external line boundaries, possibly head specified, normal flux specified, and so on. And then between domain A and the triple layer area of BCD, there's an interdomain boundary that goes around here. But we have other boundary conditions to consider at the bottom of the model and at the top. So on the top, it would be this light blue surface here and this pink colored surface here. On the bottom, it would be the gray surface here and the green surface here. And we need to apply boundary conditions basically at the top of the topmost level. That's the blue and the pink. And at the bottom of the bottommost level, that would be the gray and the green. There are two types of boundary conditions that can be applied at the top and bottom. One is flux specified, which would be units of length per time or discharge per area, much like a precipitation number. And that's usually used for recharge at the top of your model or an impermeable zero flux out the base of the model. That could be a finite flux out the base. That's also possible, but less common. The second kind of top or bottom condition is a head-dependent flux. And in that case, you specify a head toward which the top domain or bottom domain is leaking. And this is used most often for upward leakage out of the topmost layer to a surface water that has a fixed head. You can also use it at the bottom of the model for downward leakage to a deeper aquifer or known head that is below the bottom layer in your model. In Anaqsim, you specify these top and bottom conditions over the area that is spanned by a domain, over the area that is spanned by a polygon that you define or digitize. And usually these are constant values that apply over a domain or a polygon, but you can also define a non-constant value either for the flux rate or the head in a head-dependent flux. And we'll talk about that later. Let's run through a few examples for this hypothetical model that we've sketched here. We could have over the top of the model in the domain A area, this light blue surface, a specified top flux, a recharge rate, let's say it's Y. And at the bottom of A, this gray area, we specify a bottom flux of 0, so impermeable. In the 3-layer area here, we could specify a top flux that's different, say X, and a bottom flux of 0 out the bottom in this green surface here. And we could choose the area of domain B or the area of domain C or the area of domain D. They're all the same area when you look at it from above, but we only need to choose one of those three, because whatever domain you choose, the top condition you're applying applies at the top of the topmost layer in that area. So even if we chose domain D, say, the top condition would apply at the top of domain B because it's the topmost domain that is in the same area as domain D. And the bottom condition would apply at the bottom of domain D, whether we used domain B, C, or D to define the area over which that applies. Here's a second example with different kinds of boundary conditions at the top. In the light blue area at the top of domain A, we could specify a head-dependent flux. Maybe this area is a big wetland that has a fixed head of H sub S. And again, we might have a flux specified condition at the bottom of domain A, but rather than have it 0 and impermeable, we have it some finite value Z leaking down to some deeper level. In the area of domains B, C, and D, we could specify a top flux of X. Maybe this is an upland that is stands proud of the wetland, and it has recharge coming in at rate X. And at the bottom, we could specify the same bottom flux Z leaking to deeper layers. That's another example. So here's a third example that is a bit different and makes use of a polygon area in addition to domain areas for specifying top and bottom conditions. In domain A, we have a specified top flux, a recharge rate of Y, and a specified bottom flux of 0, an impermeable base. And in domains B or C or D, one of the three, you would specify a top flux of X, a recharge rate, but different than out here in domain A, and a bottom flux of 0, so impermeable again down here. Now the polygon E here, we are using a polygon to define a special condition there. Let's say that is a pond, and we have head-dependent flux up into that pond from the underlying aquifer, and we're going to specify a head H sub S for that surface water. And in the area of polygon E, which ripples through domains B, C, and D down to the area directly below this polygon, at the bottom of domain D, that's where the bottom condition for this specification would apply. We will use the same bottom specified flux of 0 in that area. So everything is specified either by a domain area or the area of a polygon, and polygons overwrite domain specifications. So we had a domain B, let's say, specification, but when we added a polygon E, it overwrites the boundary conditions that would have been there had we not put in the polygon. These top and bottom boundary conditions that we've talked about, say a recharge rate on the top or a head-dependent flux to a surface water, these are not discharges along points or lines, line boundaries or wells. They are discharges that occur over an area. So we need an area sink element, and we'll get into that next. Let's look again at the general equation in terms of the aquifer discharge potential here, this top equation. We are summing up contributions from well elements, line sink elements, or line elements, and area sinks. And the Laplacian, that's what this symbol is, of that summation is going to equal gamma, where gamma hopefully approximates the distributed source and sink terms, leakage out the top, leakage out the bottom, and flux into storage in a transient model. Now our well and line elements have a Laplacian equal to 0. So this gamma, what we call extraction, is going to all come from an area sink element. And that area sink may or may not be a function of position. If it's uniform over the area of a domain, then it's just a constant, this gamma. But if it's spatially variable over the area of a domain, what we call a spatially variable area sink, then the extraction rate here varies with location. There are two kinds of area sinks implemented in Anaqsim: a uniform area sink, where that extraction rate gamma is fixed and constant over the area of a domain. It doesn't matter what your location is, you have a constant rate. And it is useful, but it has these constraints. You must satisfy all three of these bullet items here in order to make use of the uniform area sink. It must be a steady state flow, not transient, because in transient flows, the fluxes in and out of storage are never going to be uniform. They're going to be high near features like streams and wells that are changing, and low elsewhere. It must be single layer. And that's because when you have vertical leakage between multiple layers, those are never going to be uniformly distributed, except in some absurd kind of a model. So any realistic model, multi-layer, forces you to use a spatially variable area sink. And if the flux that you specified at the top or bottom of your model is going to vary with location, you can't use this. So you must satisfy all three of these conditions in order to make use of a uniform area sink. Single layer, steady, and a constant flux applied at both the top and the bottom. The great advantage of a uniform area sink is it's really a cinch computationally. It adds very little computation to do that. And it is quite handy for a single layer steady model to apply a uniform recharge rate. And it's actually fairly common. The other kind of area sink is a spatially variable one, what I'll call SVAS, short for spatially variable area sink. And with that, this extraction rate varies with location in the domain. And you must use an SVAS if any of these 4 bullet points apply. If it's transient, if it's multi-level, or if the top or bottom flux rate is spatially variable. Maybe you want to have varied rates of recharge across your domain. You'd need a SVAS. If the top or the bottom condition is a head-dependent flux, you're going to need a SVAS because that will not lead to a uniform distribution of leakage. The upside is that you can handle all these kind of conditions. The downside is it involves substantially more computation than a uniform area sink, but well worth it because you can have much more capability here. Here's an example of a good application for uniform area sinks. This model at right here has an outer domain with a fixed recharge rate coming in the top. And by the way, this is a single level steady state model. And within this green polygon is another domain that is a recharge basin where it's a substantially higher rate of recharge, but over the area of that particular domain, the recharge basin domain, it is uniform. So each domain has a constant rate of recharge, which means a constant extraction gamma, but these two different domains have differing rates. So if we were to make a plot of the leakage out the top of level 1 along this yellow line, that's what we've got below here. Out in the outer area, we have a small rate of recharge, this fixed line here, it's non-zero, and again out the other side. But in the area of the recharge basin, we have a much larger, order of magnitude larger recharge rate going on there. And you can see in the contours of head, which are blue, that you've kind of created a bit of a bulge or a mound due to that added recharge in the recharge basin. So that's a good example of how you might use uniform area sinks to simulate mounding due to, say, a recharge basin. Within any one domain, the distribution of extraction, this gamma, that is created by a uniform area sink or a spatially variable one, is smooth and continuous. But where you cross from one domain to another, the extraction can jump across those interdomain boundaries, and sometimes that's what you want. Here's an example of a case where you do want that. Here's a cross section showing an unconfined sandy aquifer that has recharge coming in the top, an impermeable base, and then we've got a broad river that has leakage into it from the aquifer from below. So if you think about this location here, just to the left of it and out in here, we have a uniform rate of recharge coming in the top. But once we hit that bank, we've got recharge going out of the aquifer and into the surface water, the river. And that rate of recharge from the aquifer back to the surface water will vary. It'll be high right at the shorelines and decrease as you go towards the middle of it and then get high again at the other shoreline. And I made a single layer model of this kind of situation and a plot of the leakage out the top of level 1 in a line that goes across the river. So out here in the area outside the river bank, on this area and on this area, we have a uniform area sink giving us a fixed rate of recharge, and hence these lines that are a bit negative, below zero, for the recharge. Under the river, we have a spatially variable area sink with its highest rates going the opposite direction, a positive number, near the shoreline of the river and decreasing in kind of a saddle in the middle of the river, and then again a peak at the shoreline over here. And there is this abrupt discontinuity when we transition from the domain, and it's a separate domain that lies underneath the river that has a SVAS, to the surrounding domain that has a uniform area sink. And we have this abrupt jump, which is what you want to achieve. In Anaqsim, the top or bottom condition, either a flux or a head, in the case of a head-dependent flux, is usually specified as a constant number over the area of a domain or of a polygon within the domain, but it can also be an irregular surface where the flux rate, for example, would vary with position in the domain or within the polygon. And to do that, Anaqsim uses a radial basis function interpolator that Hardy in 1971 created, and I think his main application at that point was for contouring point data to make contour maps. But it's a good algorithm and it works well, and it's implemented in Anaqsim. So you have a series of triads where you have location x, y, and your point value. In this case, it'd be a head for head-dependent flux. And you have a whole series of those, And the head at any one location, x and y, is given as this sum for n different triads of the head at that particular spot times the radial distance from x comma y to the x1, y1, for example, plus a constant. And r sub I here is the radial distance from x comma y, where you're evaluating this interpolated function, to a particular data triad, say x1, y1, h1. Okay, and that's summed up. And if you specify only 3 points, 3 sets here, 3 triads, then Anaqsim will use a planar surface instead of using this Hardy interpolator. But if you have 4 or more points, it uses this equation here, and it creates an irregular but smooth surface that goes through all the data points. Here is an example of one of those radial basis function surfaces using the Hardy interpolator. At each of these red points, red circles here, there is a data triad, an x comma y comma value, say. And I've just plugged in random values within some range here. And this just illustrates the kind of surface you will get. It will go through the value exactly at each of these data points, and then it will be a smooth surface in between them. So you can define any kind of an irregular surface, and usually they'll make a bit more sense than this, which is just random values. You can create a sloping surface with just 3 data points, or you can create a fairly complex surface with dozens or even 100 data points.